Hello, welcome back. Wherever you are tonight, bedroom, couch, train, somewhere in between, I'm glad you've found your way here again. Settle in. Get comfortable in whatever way comfortable means for you tonight. Adjust the blanket, dim the light, let your shoulders drop a little from wherever they've been holding tension all day. You don't need to remember any of this by morning. You don't need to take notes. This is a place for drifting, not for studying. If your eyes close partway through, that's not a failure of the format. That's the format working exactly as intended. And if you're new, if this is your first night here, welcome to Late Space. We talk about big, slow things, gently, until you fall asleep. If you find that you like having a place like this, a like or a subscribe helps other people find their way here too, on their own sleepless nights. No rush on that. Do it tomorrow, or never. We'll still be here. Tonight, we're going somewhere far. Past the planets. Past Neptune, which we visited not long ago. Out into a region of the solar system that most people learnt about, if they learnt about it at all, as a kind of footnote, a vague ring of icy debris out past the last planet, home to Pluto, and not much else. That picture is wrong. Not wrong in a small way. Wrong in a way that scientists have only really come to appreciate in the last few years, as new instruments and new missions have started returning data that doesn't fit the old tidy story. The Kuiper Belt is bigger than you think. Possibly much bigger. Possibly twice as big, with an entire second belt out past the one we already knew about, separated by a strange gap that nobody can yet explain. And the implications of that, for how the solar system formed, for what might still be out there, for how unusual or ordinary our solar system actually is compared to others, are still being worked out in real time by scientists who are almost as surprised as you're about to be. Let's go slowly. Close your eyes whenever you want. We'll get there together. Let's start with what most people think they know, because it's a reasonable place to start, and because most of it is true, even if it turns out to be incomplete. Beyond Neptune, beyond that last blue ice giant we talked about a little while ago, sitting 4.5 billion kilometers from the Sun, the solar system doesn't simply end. There isn't a wall or a sudden drop into nothingness. Instead, there's a vast donut-shaped region of small icy bodies, leftover material from the formation of the solar system, orbiting the Sun in a slow, cold, patient ring. This is the Kuiper Belt. Named after Gerard Kuiper, a Dutch-American astronomer who, in 1951, proposed that such a region might exist, though, in one of those quiet ironies that shows up so often in the history of science. Kuiper himself didn't think any of these objects would still be there by now. He thought they would have been swept away long ago, scattered by the gravity of the outer planets, leaving the region empty. He was wrong about the emptiness, and right, in a sense, about there being something worth looking for. It took until 1992 for anyone to actually find one. An astronomer named David Jewett and a graduate student named Jane Liu spent years searching, painstakingly comparing photographic plates of the same patch of sky taken nights apart, looking for a single point of light that moved just slightly against the fixed background of stars. In August of that year, they found it, a small icy world, later named Albion, orbiting the Sun far beyond Neptune. The first confirmed Kuiper Belt object since Pluto itself, which had been discovered all the way back in 1930. Though at the time nobody understood that Pluto was the first known member of an entire population of similar worlds, rather than a strange anomaly all on its own. Since then, the count has grown into the thousands. We now believe there are more than 100,000 Kuiper Belt objects larger than 100 kilometers across, and many millions of smaller ones, all orbiting out in that cold, donut-shaped expanse. The traditional picture, the one most textbooks still describe, places this belt starting at about 30 astronomical units from the Sun, roughly where Neptune orbits, and extending out to about 50 astronomical units. An astronomical unit, just so the number means something, is the average distance from the Earth to the Sun, about 150 million kilometers. So the Kuiper Belt in this picture spans from 30 to 50 times that distance. A wide, cold ring of ice and rock, 20 times wider than the asteroid belt between Mars and Jupiter, and vastly more massive. And then, at 50 astronomical units, according to this traditional picture, it just stops. Abruptly. The number of objects drops off sharply, almost to nothing, in a way that nobody fully expected and nobody has ever fully explained. This sudden drop-off has a name. Astronomers call it the Kuiper Cliff. Let's sit with that phrase for a moment. The Kuiper Cliff. It's an evocative image. The edge of something falling away, the solar system's outer material simply running out, the way a coastline runs out into open ocean. For decades, this was treated almost as a settled fact. The Kuiper Belt extends to about 50 astronomical units, and then it ends, and beyond that is comparative emptiness, at least until you reach the much more distant, much more sparsely populated Oort cloud, 1,000 times farther out still, a sphere of icy bodies surrounding the entire solar system like a faint ghostly shell. But here's the thing about a cliff in a scientific model. It's the kind of feature that should make you suspicious. Nature, on the whole, doesn't love sharp edges. Most distributions in physics and astronomy taper off gradually, a slow fade rather than a sudden stop. When you find a sharp cliff instead of a gradual decline, it usually means one of two things. Either something physical is actually creating that edge, some process actively clearing out the material beyond a certain point, or, and this is the less dramatic but often more likely explanation, you simply haven't looked far enough, or carefully enough, to see what's actually there. For a long time, astronomers favoured explanations in the first category. Maybe the gravity of Neptune, over billions of years, had swept the region clean beyond 50 astronomical units. Maybe there hadn't been enough material that far out in the original disk of gas and dust the solar system formed from. Maybe some unseen planet, and we'll talk about this, because it's one of the most tantalizing threads in this whole story, was gravitationally shepherding material in a way that created the cliff. But there was always a nagging alternative explanation sitting quietly in the background. Maybe we just hadn't looked far enough out yet, because objects that far away are extraordinarily faint, extraordinarily hard to detect, and our telescopes, however good, have limits. It's a bit like standing at the edge of a large dark field at night with a flashlight, and concluding the field ends exactly where your flashlight beam stops illuminating the grass. The field might genuinely end there, or your flashlight might just not be strong enough to show you what's further out. Wherever you are, I hope you're comfortable. Let's pause here and breathe for a moment, because we're about to go further out than most descriptions of the solar system ever take you, and it helps to feel settled before the distances start getting strange. I want to tell you about a spacecraft. Its name is New Horizons, and it has spent more than 15 years now becoming one of the great storytellers of the outer solar system. New Horizons launched from Earth in January 2006. Its primary mission was Pluto, at the time still officially classified as the 9th planet, though that would change later that very same year, in a reclassification that caused considerably more public outcry than most scientific reclassifications ever do. New Horizons spent 9.5 years travelling outward, and in July 2015, it became the first spacecraft to fly past Pluto, sending back images of a world far more geologically active and far more visually striking than almost anyone had expected. Mountains of water ice, a heart-shaped plain of frozen nitrogen, evidence of an internal ocean possibly still sloshing beneath the frozen crust. But New Horizons didn't stop at Pluto. It kept going, deeper into the Kuiper Belt, and in January 2019, it flew past a small, strange reddish object called Arrokoth. A tiny world shaped, when you look at the photographs, almost exactly like two snowballs gently pressed together. A contact binary, astronomers call it, two separate bodies that drifted together so slowly, so gently, billions of years ago, that they simply stuck rather than shattered. Arrokoth remains the most distant object any spacecraft has ever explored up close, and it offered an extraordinary, almost untouched snapshot of what the building blocks of planets looked like at the very beginning of the solar system, frozen in time for 4.5 billion years. And then New Horizons kept going. It's still going now, more than 5 billion miles from Earth, more than 60 times farther from the Sun than our own planet is. Most of its instruments have been put into a kind of hibernation to conserve power and extend the mission, but a handful remain active, including a small, elegant instrument called the Student Dust Counter, designed, built, and operated almost entirely by university students, the first instrument on any NASA planetary mission to carry that distinction. The Student Dust Counter does something simple. It counts dust. Tiny grains of interplanetary material, the microscopic debris produced when larger objects collide out in the dark. And what it has been finding. As New Horizons has travelled outward through the supposed edge of the Kuiper Belt, has surprised almost everyone who's looked at the data. The dust isn't stopping. Here's why that matters, and it's worth taking slowly, because the logic is elegant once you see it. If the Kuiper Belt genuinely ends at around 50 astronomical units, if that's really where the material runs out, then the rate of collisions between objects out there should fall off as New Horizons travels past that point. Fewer objects means fewer collisions, means less dust being produced and drifting through space. The dust counter should have shown a steep decline as the spacecraft crossed from 45 to 55 astronomical units, the region where the traditional Kuiper Belt was supposed to thin out and end. Instead, across 3 years of continuous measurement, the dust counter kept registering impacts at rates that didn't decline. The readings simply didn't match what the models predicted. Something out there, beyond the supposed edge, was still producing dust. Which means something out there was still colliding. Which means something out there still exists in meaningful quantities. The lead researcher on this finding, a graduate student named Alex Donor who runs the dust counter instrument, described it in terms that capture, I think, exactly the right tone of careful astonishment scientists bring to a genuine surprise. Every new observation could lead to a discovery, and this one suggested an entirely new population of objects, out past where anyone expected them to be. It's a bit like sweeping a dark room with your hand, expecting to find the wall, and instead finding that the room just keeps going. Around the same time the dust counter was returning its puzzling readings, a separate group of astronomers was independently arriving at a strikingly similar conclusion, using an entirely different method. This group, led by an astronomer named Wesley Fraser, was using the Subaru telescope, an enormous 8.2-meter telescope perched on the summit of Mauna Kea in Hawaii, one of the most powerful optical and infrared instruments on Earth. Their original purpose was practical and somewhat modest. They were searching for new Kuiper Belt objects that New Horizons might be able to photograph or study as it continued its journey outward, looking for promising targets in the spacecraft's path. What they found instead was a population of objects nobody was quite looking for. Objects orbiting the Sun at distances of 70 to 90 astronomical units, far beyond the traditional 50 AU edge of the Kuiper Belt. Far enough out that, under the old picture, there shouldn't have been anything substantial there at all. And it wasn't just a stray object or two. It was, as Fraser and his colleagues described it, a significant mass of material out there, enough to suggest this wasn't noise or a fluke, but a genuine population of bodies that had simply gone undetected because they were so faint, so distant, so far past the limits of what most previous surveys had been sensitive enough to find. Fraser's reaction to this, when he talked about it afterward, carried a note of something close to relief mixed with surprise. For years, he said, our solar system's Kuiper Belt had seemed unusually small compared to the debris disks astronomers have observed around other stars. Disks that, when we look at them through telescopes like ALMA in Chile, often extend for hundreds of astronomical units. vastly larger than the 50 AU edge our own solar system supposedly had. It had become, in a quiet way, a small embarrassment of solar system science. Why was our own Kuiper Belt so comparatively tiny and unusual, when other planetary systems seemed to build such much larger ones? This new finding offered an answer. Maybe our Kuiper Belt was never actually that small. Maybe we'd simply been looking with a flashlight that wasn't strong enough to see all the way to the back of the field. Now here's where the story gets stranger, and where I want you to lean in a little, even as you're drifting, because this is the part that nobody fully expected and nobody can yet fully explain. Between the traditional Kuiper Belt, the one ending around 50 AU, and this newly discovered population of objects starting around 70 to 90 AU, there appears to be a gap. A genuine, measurable gap, roughly 10 astronomical units wide, between about 50 and 60 AU, where there seem to be comparatively few objects at all. So the picture isn't simply the Kuiper Belt is bigger than we thought, extending smoothly further out. The picture is stranger than that. It's the Kuiper Belt extends to about 50 AU, then there's a relatively empty gap, and then there's a second, separate population of objects starting again around 70 AU and continuing outward from there. A second Kuiper Belt, separated from the first by a gap that, as one physicist working with the New Horizons data put it, something one way or another is responsible for maintaining. That phrasing is doing a lot of careful, honest work. Something is responsible for maintaining that gap. Not we know what's responsible, just something is. The gap isn't random emptiness. Gaps like this, in disks of orbiting material, usually means something is actively keeping them clear. In other planetary systems, when astronomers observe gaps like this in the dusty disks surrounding young stars, the explanation is often straightforward. A planet is orbiting within the gap, its gravity sweeping up or scattering away the material in its path, like a plough clearing a furrow through snow. We've seen this pattern directly, in disk after disk, around other stars. But here's the puzzle. In our own solar system's newly discovered gap, between 50 and 60 astronomical units, no planet has been found. Nothing massive enough to be doing the ploughing has shown up in any survey, despite considerable effort to look for exactly that. Which leaves us with a genuinely open question, sitting right there in our own cosmic backyard. In a region of space we are only now beginning to properly map. Wherever you are, I hope you're still comfortable. This is the kind of mystery that's fun to sit with rather than solve immediately, so let's not rush toward an answer. Let's just hold the shape of the question for a while. There are, broadly, a few candidate explanations on the table, and none of them are fully confirmed. One possibility is that there genuinely is an unseen planet out there, gravitationally responsible for the gap, something perhaps the size of Earth or Mars, too small and too distant and too dim to have been spotted yet by any survey, but massive enough to clear a corridor through the surrounding debris over the 4.5 billion year history of the solar system. This idea connects in an interesting way to a much more famous and much more hotly debated hypothesis that's been floating around for the better part of the last decade. The idea of a so-called Planet 9, a hypothetical large planet, perhaps 5 to 10 times the mass of Earth, orbiting the Sun at extraordinary distances, inferred not from direct observation, but from the strange. Clustered orbits of a handful of distant Kuiper Belt objects, whose paths seem to be subtly shepherded by the gravity of something we haven't yet directly seen. To be clear, the gap between 50 and 60 AU and the hypothesized Planet 9 are not necessarily the same story. Planet 9, if it exists, is generally thought to orbit much farther out, hundreds of astronomical units from the Sun, well beyond even this newly discovered second belt. But both mysteries share a common thread: subtle gravitational signatures in the outer solar system, hinting at the presence of something we haven't yet caught in a telescope's gaze. The solar system, it seems, is still capable of hiding large things from us simply by virtue of being extraordinarily big and extraordinarily dark. A second possible explanation for the 50 to 60 AU gap doesn't require any unseen planet at all. It's possible the gap is a fossil, a structural relic left over from the earliest days of the solar system 4.5 billion years ago, when the young sun was still surrounded by a swirling disk of gas and dust, and waves of pressure rippling through that disk could have carved channels and gaps into the material. The way ripples on a pond's surface can leave temporary furrows in sand beneath shallow water. In this picture, the gap isn't being actively maintained by anything today. It's simply an ancient scar, frozen in place since the solar system's infancy, never quite filled back in because there was never enough material or enough time for it to smooth over. A third possibility, somewhat less dramatic but still scientifically interesting, is that the gap isn't a gap in actual material at all, but a gap in our ability to detect it. That there are objects there, just smaller and fainter and harder to spot than the populations on either side, and as our telescopes and surveys improve, the apparent emptiness will fill in. We don't know which of these is correct. Possibly more than one is true simultaneously. The honest, current scientific position is there's a real and curious gap out there, and nobody is yet sure why. I want to step back here for a moment, because I think it's worth feeling the full weight of what's actually happening in this story, beyond just the individual facts. We are right now in the middle of one of those rare periods in planetary science where the basic outline of something we thought we understood is being redrawn in real time. Not replaced wholesale, the Kuiper Belt as traditionally understood, from 30 to 50 AU, remains real, remains well documented, remains home to Pluto and dozens of other dwarf planets, and tens of thousands of catalogued smaller bodies. But the edges of the picture, the boundary of what we thought was the outer limit of the solar system's structured disk of material, are turning out to be considerably less final than anyone assumed. It's a bit like spending your whole life believing a familiar lake has a shoreline you've walked the entire perimeter of, only to discover, decades later, that there's a second hidden lake just past a ridge of trees you'd never bothered to climb over, connected to the first by some narrow, unmapped channel, equally large, equally real, simply unseen until now because nobody had looked in quite the right way. The solar system, it turns out, is not finished revealing itself to us. And we are not finished looking. Let me tell you something else strange that's emerged from this same broad wave of Kuiper Belt research, because it connects to a question that sounds almost whimsical but turns out to be deeply important. Why do so many Kuiper Belt objects look like snowmen? I mentioned Arrokoth earlier, that small reddish world New Horizons photographed in 2019, made of two lobes gently fused together, like two snowballs pressed lightly into one shape. For years, this peculiar two-lobed structure puzzled scientists. Why would objects out in the cold, slow-moving outer solar system so often end up shaped like this? Recent research has been building a compelling answer, and it has to do with how these objects actually formed, billions of years ago, in the swirling disk of gas and dust that surrounded our infant sun. The traditional model of how small bodies form, through countless violent collisions, smaller bits of rock and ice slamming together over millions of years, gradually accreting into larger bodies, turns out to struggle to explain these gentle, fused, snowman-like shapes. A violent collision history tends to produce battered, irregular, cratered objects. Arrokoth, when New Horizons photographed it up close, showed remarkably few craters and a startlingly smooth, gently fused structure, evidence of an extremely slow, extremely gentle joining, rather than a series of violent impacts. The newer explanation, called the streaming instability hypothesis, suggests something quite different, and I think genuinely beautiful. Rather than forming through collision after violent collision, these objects may have formed when small particles in the early solar system's disk, tiny grains of ice and dust, became gravitationally concentrated in certain regions, clumping together not through impact but through a kind of slow, gentle gravitational collapse, the way flour might settle and clump in a sieve if you shake it just the right way. Under this model, pairs or even trios of bodies could form together, gently side by side, eventually drifting close enough to touch and merge without ever colliding violently at all. This connects to something else researchers have recently found using the Hubble Space Telescope, evidence not just of binary Kuiper Belt objects, two bodies orbiting each other, but of triple systems. Three icy bodies, gravitationally bound together, slowly circling one another out in that cold, distant region. A potential second such triple system, found around an object called Algira, suggests these complex multi-body arrangements might not be rare exceptions out there, but a fairly common outcome of how this entire population of small worlds came to be. The Kuiper Belt, in other words, isn't just bigger than we thought. It's also stranger, gentler, and more intricately structured than we thought, a place where worlds formed not through violence, but through a slow and patient drifting together, the cosmic equivalent of snow settling silently overnight. Wherever you are, I hope you're comfortable. Let's breathe again for a moment, because there's a lot of strangeness accumulating here, and it's worth letting it settle rather than rushing past it. I want to take you back to scale for a moment, because scale is where this story really earns the word bigger. The traditional Kuiper Belt from 30 to 50 AU is already an enormous structure, 20 times wider than the asteroid belt between Mars and Jupiter, and estimated to contain 20 to 200 times more total mass. If the new discoveries hold up, if there really is a second population of objects extending out to 80, 90, perhaps more astronomical units separated from the first by that mysterious gap, then the structured, disc-shaped region of debris surrounding our Sun isn't merely large. It potentially nearly doubles in extent. The solar system's outer disk, rather than ending crisply at 50 AU, may continue, with an interruption, out to nearly twice that distance. And even that vastly expanded outer disk is still nothing compared to what lies beyond it. Beyond even this newly discovered second Kuiper Belt, scientists believe there is the Oort cloud, 1,000 times more distant still, not a flat disk but a vast spherical shell of icy bodies, theorized to extend out to somewhere between 50,000 and 200,000 astronomical units from the Sun. We have never directly observed an Oort cloud object. Its existence is inferred almost entirely from the orbits of long-period comets, those rare icy visitors that swing through the inner solar system only once every few thousand or even million years, on orbits so vast that their origin can only be explained by a reservoir of material that distant, that ancient, that quietly enormous. If the solar system's planets and the traditional Kuiper Belt are like a house, rooms you could, in principle, walk through and map, then the newly discovered second belt is like discovering an entire additional wing of that house you never knew was there. And the Oort cloud, sitting even farther out, is like discovering that the house itself sits inside the grounds of an estate so large you could walk for a year in any direction and still be on the property. We live, it turns out, inside something considerably larger than the picture most of us grew up with. There's a question worth pausing on here, because I think it connects this whole story to something deeply human, something underneath the astronomy. Why does it matter how big the Kuiper Belt actually is? It's not, on the face of it, a question with obvious stakes for daily life. Nobody's morning commute changes based on whether there's a second belt of icy objects 70 astronomical units from the Sun, and yet I think the question matters in a way that goes beyond practical consequence, and it has to do with the story we tell ourselves about where we live. For most of human history, where we live meant a town, a valley, a coastline. Then it meant a country, a continent. Then, slowly, painfully, it meant a planet, a single small sphere suspended in space. which took centuries of careful observation and not a small amount of persecuted genius to fully accept. Then it meant a solar system, then a galaxy among countless other galaxies, then a universe whose edges, as we discussed not long ago, we still aren't certain exist at all. Each time that picture has expanded, something in the human sense of place has had to expand along with it. Not painlessly, not always gracefully. But each time we've found that being smaller than we thought, living inside something larger than we thought, has tended eventually, after the initial vertigo passes, to deepen rather than diminish the sense that being here, asking these questions, noticing these things, is worth doing. The discovery that our own solar system's outer reaches are more extensive, more structured, more mysterious than we believed even 5 years ago is a small instance of that same pattern. We are not just slightly revising a number on a chart. We are discovering that the place we live, the system of worlds orbiting our particular star, is more interesting, more architecturally complex, more full of unanswered structure than the textbooks suggested. And there is something quietly thrilling, I think, in realizing that even something as close to home as our own solar system's edge is still capable of surprising the people studying it. We are not finished mapping our own neighborhood. And there's something comforting in that, in a way I find hard to fully articulate. The universe declining to be fully known, even in the places nearest to us, leaving room for wonder that doesn't require travelling to distant galaxies to find. Let me tell you about what's coming next, because this story isn't finished, and the next few years are likely to bring real answers to some of these open questions. Leslie Fraser and his colleagues have continued their observations with the Subaru telescope, returning to Mauna Kea with improved instrumentation, a new optical filter specifically designed to detect fainter, smaller objects than their earlier surveys could see. If the second Kuiper Belt is real, if it's a genuine populated structure rather than a statistical fluke, then more careful. More sensitive surveys should reveal more than a dozen additional distant objects out there. If that expectation isn't met, if the deeper searches come back comparatively empty, then, in Fraser's own words, something has been completely missed in our understanding, and the puzzle deepens rather than resolves. Meanwhile, an enormous new instrument is coming online that promises to transform this entire field of research. The Vera C. Rubin Observatory, perched in the mountains of Chile, is designed to conduct the most comprehensive survey of the night sky ever attempted, repeatedly imaging the entire visible sky every few nights, cataloguing everything that moves or changes for a full decade. Where previous surveys for distant Kuiper Belt objects involved astronomers carefully, manually searching small patches of sky, the Rubin Observatory will essentially photograph everything, continuously, and use automated systems to flag anything moving against the background of fixed stars. Some projections suggest this single observatory could discover millions of new solar system objects over the course of its survey, comets, asteroids, and crucially, vast numbers of new Kuiper Belt objects, potentially including many in that mysterious gap region and many more in the newly discovered outer population. And New Horizons, remarkably, is still out there, still travelling, still listening with its small student-built dust counter, adding a few more data points every year to a dataset that has already overturned assumptions nobody thought needed revisiting. There has been quiet discussion within NASA and the broader planetary science community of identifying a third flyby target for the spacecraft, another distant Kuiper Belt object the aging probe could be steered toward and photographed up close, the way it photographed Arakoth, extending its extraordinary tour of the outer solar system even further into territory no human-made object has ever directly examined. We are, in other words, standing at the very beginning of a period of discovery in this region, not the end of one. The picture we have right now, a first belt, a gap, a second belt, an uncertain and possibly planet-shaped explanation for the gap, is likely to look meaningfully different, more detailed, more resolved within the next decade, possibly within the next few years. Wherever you are, I hope you're still comfortable. We're well past the midpoint now, and the night is doing what it does, getting quieter, the words slowing down to match it. I want to talk for a moment about what it actually feels like, scientifically, to discover that your flashlight wasn't strong enough. There's a particular kind of humility built into observational astronomy that I think is worth naming directly, because it's different from the humility involved in, say, admitting you were wrong about a calculation. Astronomers weren't wrong exactly about the Kuiper Belt ending around 50 AU. Given the instruments available, given the surveys conducted, given the detection limits of the telescopes used, the data genuinely did show a steep drop-off there. The conclusion that the belt ended was a reasonable, careful, honestly drawn inference from the best evidence available at the time. What's changed isn't that the old evidence was false. What's changed is that better evidence has become available, gathered with more sensitive instruments, conducted with more patient and more deeply searching surveys, and that new evidence reveals more of the picture than the old evidence could. This is, in a sense, the entire shape of observational science, played out again and again across history, at every scale from subatomic particles to galaxy clusters. You look as far and as carefully as your tools allow. You draw the most honest conclusion the data supports. And then, sometimes years or decades later, someone builds a better tool, looks a little further, a little more carefully, and finds that the universe had more to show you than it had previously been able to. This isn't a flaw in how science works, it's the entire design of it. Every map of the unknown is provisional, not because scientists are careless, but because the unknown, definitionally, exceeds whatever tools currently exist to chart it. The Kuiper Cliff wasn't a mistake. It was an honest boundary, the edge of what could be seen, mistaken, understandably, for the edge of what exists. And now that boundary has moved, and it will likely move again. I want to bring Pluto back into this story for a moment, because Pluto's own history is, in miniature, almost exactly this same lesson. When Pluto was discovered in 1930 by a young astronomer named Clyde Tombaugh working at the Lowell Observatory in Arizona, it was treated, almost immediately, as the ninth planet, a solitary. Distant world, alone out at the edge of the solar system, fundamentally different in kind from anything closer in. For 62 years, that was the picture. Pluto, alone, the last planet, the outer boundary of where the solar system's structured material existed. Then, in 1992, Albion was discovered. Then more objects. Then thousands more. And slowly, patiently, over the following decade and a half, it became clear that Pluto wasn't a lonely outlier at all. It was simply the first, largest, and brightest member of an entire population of similar worlds that nobody had yet had the instruments to detect. Pluto wasn't alone out there. It had been surrounded the entire time by a vast community of icy siblings. We just hadn't yet built the telescopes capable of seeing them. In 2006, the International Astronomical Union formally reclassified Pluto as a dwarf planet rather than a full planet, a decision that even now, nearly 2 decades later, still generates passionate disagreement among both professional astronomers and members of the public who grew up with Pluto firmly fixed in the planetary lineup. Whatever you think of the classification decision itself, and reasonable, well-informed people disagree about it, the underlying scientific story is genuinely remarkable. Pluto turned out not to be a strange, isolated exception, but the first visible representative of an entire previously unknown region of the solar system. The same pattern, the exact same shape of discovery, may now be playing out again, one layer further out. First we found a few stray objects beyond 50 AU. Then a meaningful population of them. Then a gap. then evidence the gap is real and structured rather than accidental. We may be, right now, in roughly the same position relative to this second Kuiper Belt that astronomers were in during the early 1990s, just after Albion's discovery, just beginning to suspect that what looked like an edge was actually a doorway. Let me tell you something quieter now, something that's less about the science and more about what it feels like to think about all of this at night, in the dark, the way we're doing right now. There is a vast structure out past Neptune, a donut-shaped disk of icy worlds that has been there, largely undisturbed, for 4.5 billion years. It was there before there was a Pluto to find, before there was a Tombaugh to find it, before there was a species capable of building telescopes at all. It has been quietly orbiting, in the deep cold and the deep dark, for the entire span of the solar system's existence. Through every ice age, every mass extinction, every rise and fall of every civilization that has ever existed on the small blue planet much closer to the sun. And it has the entire time been more extensive, more structured, more architecturally rich than anyone realized, right up until a graduate student's dust counter and an astronomer's careful telescope survey both, independently, around the same handful of years, started returning data that didn't fit the old picture. There's something almost tender in that, if you let yourself feel it. The universe wasn't hiding anything from us out of malice or mystery for its own sake. It simply continued being exactly what it was, indifferent to whether we'd noticed yet, while we slowly, patiently built the tools necessary to notice. The Kuiper Belt's second population wasn't created by the discovery. It was always there. We simply arrived, finally, at the part of the conversation where we could hear it. That's most of what astronomy actually is, when you strip away the technical vocabulary. Catching up to things that have been true for a very long time. I want to mention briefly something that connects this whole story back to a much bigger question, one that touches on whether our solar system is unusual, or whether it's actually fairly typical among the countless other planetary systems scattered throughout our galaxy. Astronomers studying young, still forming planetary systems around other stars, using instruments like the ALMA radio telescope array in Chile, which is exquisitely good at detecting the faint glow of dust in these distant systems, have found that debris disks like our own Kuiper Belt are extremely common. And critically, many of these other debris disks show exactly the kind of structure we're now finding hints of in our own solar system, multiple rings separated by gaps. Extending out to hundreds of astronomical units from their parent stars, far larger than our solar system's traditionally understood 50 AU edge. For years, this comparison made our own solar system look unusual, almost stunted by comparison, a strangely small, strangely simple debris disk next to the elaborate multi-ringed structures seen around other young stars. It was, as Fraser put it, one of the odd things about our particular corner of the galaxy. How comparatively tiny our outer disk seemed to be. If this newly discovered second Kuiper Belt holds up under further study, if it really does extend our solar system's structured outer disk out to 80 or 90 astronomical units, with a genuine gap structure resembling the gaps seen around other young stars, then our solar system stops looking like an outlier and starts looking considerably more ordinary. Not a strange, stunted exception to how planetary systems usually form, but a fairly typical example of the same architecture astronomers see again and again around other stars, simply observed, until now, with instruments that weren't quite sensitive enough to reveal its true extent. There's something quietly comforting in that too, though it's a different kind of comfort than wonder at scale. It's the comfort of belonging. Our solar system, it turns out, may not be the small, unusual, slightly disappointing example we once thought it was, sitting modestly among the universe's other more elaborate planetary systems. It may simply be one more ordinary example of the same beautiful pattern that plays out, again and again around stars throughout the galaxy, disks within disks, gaps within structure, icy worlds gathered in patient rings around their parent suns. We are not unusual. We are, perhaps, simply still being fully discovered, even by ourselves. Let's come down slowly now. Let the details settle, like snow falling without much sound. Here is what we actually know, as carefully and honestly as I can put it. The Kuiper Belt, as traditionally understood, extends from about 30 to 50 astronomical units from the Sun, and is home to Pluto, to dozens of other dwarf planets, and to hundreds of thousands of smaller icy bodies, the leftover building blocks from the formation of our solar system 4.5 billion years ago. Beyond 50 astronomical units, the population of objects appears to drop sharply, the so-called Kuiper Cliff, though recent evidence increasingly suggests this drop-off may be a gap rather than a true ending. Beyond that gap, somewhere between roughly 60 and 90 astronomical units, and likely continuing further still, a new population of objects has begun to reveal itself, detected independently through direct telescope surveys and through the unexpectedly persistent dust readings of a spacecraft that was never designed to make this particular discovery, but happened to be in exactly the right place, with exactly the right small, careful instrument to notice that something didn't add up. We don't yet know what's maintaining the gap between these two populations. We don't yet know exactly how far the second belt extends, or how much total material it contains. We don't yet know whether the explanations involve an undiscovered planet, an ancient structural fossil from the solar system's infancy, or simply the current limits of our detection methods. Multiple major surveys, including an enormous decade-long sky survey about to begin in Chile, are actively working to resolve these exact questions in the coming years. What we do know is this: the solar system we live in is larger, more structured, and more architecturally interesting than the picture most of us grew up learning. The edge keeps moving. It has moved before, from Pluto being a single lonely outlier to Pluto being the first known member of an enormous belt. It is moving again now, as that belt itself turns out to extend further, and to contain more structure than anyone expected even 5 years ago. Before I let you go tonight, I want to offer you one more image to carry with you into sleep. Picture the sun, small and bright at the centre of everything, the way you might draw it as a child, a circle with a few lines radiating outward. Around it, the planets, in their familiar, carefully ordered rings. Mercury, Venus, Earth, Mars, close and warm and rocky. Then the gap and the gas giants, Jupiter, Saturn, vast and banded and ringed. Then the ice giants, Uranus and Neptune, cold and blue and distant, the last planets most of us learned by name. And then, past Neptune, instead of empty space, picture an enormous donut-shaped ring of countless small, icy worlds, pale, slow-moving, ancient, untouched by sunlight strong enough to ever warm them past the deepest cold. This is the traditional Kuiper Belt, already 20 times wider than the entire space between Mars and Jupiter. And now, picture a gap, a quiet, mysterious clearing in that ring, 10 astronomical units wide, for reasons we don't yet understand. And beyond that gap, picture another ring, fainter, more distant, more recently discovered, stretching out to 90 astronomical units and quite possibly further still. A second Kuiper Belt, hiding in plain sight, simply too dim and too far for our instruments to have properly seen it until just the last few years. And beyond even that, picture the faintest outline of something we've still never directly seen at all. A vast spherical shell of comets, the Oort cloud, extending out to distances so large that light itself would take more than a year to cross from one side to the other. All of it orbiting the same small, warm star. All of it part of the same solar system you live in, right now, tonight, in whatever room you've settled into. We have spent less than a century properly mapping any of this. We found Pluto in 1930. We found the first additional Kuiper Belt object in 1992. We're only now, in these last few years, beginning to glimpse this second, more distant belt at all. The map of our own solar system, the place we call home, in the most literal cosmic sense, is still being drawn in real time by people working right now with telescopes in Hawaii and Chile, and a small spacecraft built decades ago that just keeps going, quietly counting dust, 5 billion miles from here. The solar system is bigger than you think, and it's still revealing itself to us a little more every year. Now close your eyes if they're not already closed. Let the rings drift outward in your mind, one past another, the warm rocky worlds, the gas giants, the ice giants. The first belt, the gap, the second belt, the Oort cloud, fading into the dark. You don't need to hold the numbers. You don't need to remember which astronomical unit is which. Just let the shape of it settle. Rings within rings, structure within structure. Far more of it than anyone suspected even a few years ago, and likely still more waiting beyond the current edge of what our instruments can show us. Somewhere out there tonight, New Horizons is still travelling, quietly, patiently, 5 billion miles from home. Its small dust counter still listening for the faint signs of collisions in the dark. Somewhere in Hawaii, a telescope is pointed at a tiny patch of sky, waiting for something faint to move. Somewhere in Chile, a new observatory is preparing to watch the entire sky every few nights for the next 10 years, looking for everything that's still out there, waiting to be found. You are part of that story too, in your own quiet way. Not because you're searching for anything tonight, but because you let yourself wonder about it, here in the dark before sleep. Thank you for spending tonight here. Thank you for the curiosity that brought you this far out into the solar system, past the planets, past the familiar edges, into territory that's still, even now, being mapped for the first time. Sleep well. And somewhere out past Neptune, in the cold and the dark, the second Kuiper Belt keeps turning, slowly the way it has for 4.5 billion years, patient, ancient, and only just now, after all this time, beginning to be seen. Good night.